Let's look at rates of change for functions. Before I want to do that, I have seen a couple of questions from the homework assignment. One of the word problems, well, some of the word problems we did not model. I did that on purpose to see if you could take what we covered about quadratics and apply it in a word situation like we had seen before with linear. But I would like to walk through again, like we did with linear, an example for how we would use a quadratic word problem. Okay, so one of the problems on the assignment asked something about finding numbers whose product was a maximum or something along those lines. So here's a similar problem. We want to find two positive numbers. So the first thing we're looking for is the numbers. And then after that, we want to state what the maximum product is. So we want to find two positive numbers whose sum is 94. And the product of those two numbers that add to make 94 would be a maximum product, because there are an infinite number of combinations of numbers that we could add together to make 94, but only one of those combinations of numbers, two numbers, would have a maximum product. So whenever we're doing a word problem and we're going from words to mathematics, we need to define the variables that we are going to be using. So I'm going to let x equal the first number. And if I let y equal the second number, and if I'm going to say p is going to be the product, then we know that the sum of the numbers is 94. So x plus y has to equal 94. And we know that the product is going to be x times y. So we need this product in terms of only one variable. So if I solve for one of my variables, I can substitute over here into the product and only have it in terms of one variable. So when I solve this for y by subtracting x from both sides, I know that y equals 94 minus x. So now when I substitute in 94 minus x for the y, I now have the product as a function of only one variable. When I distribute, I get 94x minus x squared, or I get negative x squared plus 94x. And so if I were to find where the maximum occurs, we want to find the numbers that create the maximum product. So we're looking for where. I need to find the x value of my vertex. That's to find x, and then I can use that to find y. So I can do that by completing the square, factor out a negative, and then I want half of 94, half of negative 94, which is 47. And then I want to square that and give myself enough room. Negative 40. Oh, come on. And I added a negative 47 squared. So I am going to add a positive negative 47 squared. I don't have to actually calculate that. And then what I get is negative x minus 47 quantity squared plus whatever 47 squared is, which is 2209. I could have left it as 47 squared, but because I'm also going to look for the max, that's going to be beneficial. So if I were to think of the vertex, where the maximum occurs and what the maximum is. So this is where, and this is what the maximum is. So I know that at x equals 47, I'm going to have a maximum product, but I want to find the two positive numbers. So y is going to equal 94 minus the x that I found. So I can see that my two positive numbers, I'll write this in a different color. The two positive numbers whose sum is 94 and product is a max are 47 and 47. So there's my answer in words. And then the other question is state the max. So over here, the maximum product is 47 times 47, which is 2209. So technically I don't need that. I can just have the 2209. Hopefully that helps with the trying to find from word problem to quadratic to max or min. So let's look at rates of change. We have a linear function here, and what I want to look at is our average rate of change. And I'm looking at it when I'm talking about this, what I am talking about, a rate of change is just a slope. And what you're going to notice over here is that I have consecutive, equal length intervals, because my change in x is positive 3. Each time I'm changing from -6 to -3, I'm adding 3. From 3 to 0, I'm adding 3. From 0 to 3, I'm adding 3. So I have a change. My x is changing by the same distance, so I have equal length intervals. Okay, because when we're talking intervals on our graph, we're always looking in the x value. So since a rate of change is just a slope, what I'm going to look at here for my rate of change between these 2 points, change in y over change in x, my change in y is 2, because -7 to 5 is a change of 2, and my change in x we already discussed is 3. For my next interval here, I'm going to go on opposite side just so I don't get too bulky. Again, when I look at my average rate of change in y over change in x, again from -5 to -3, I have a change of 2, and -3 to 0, I have a change of 3. And then over here again, if I go from this interval, I have, again, change in y over change in x. -3 to -1 is a change of 2, positive 2, and 0 to 3 is also. So what I'm seeing is that my average rate of change over these equal length intervals is the same. So here I've got -1 to 1 is again a change of 2, and in the denominator it's a change of 3. If you are struggling to see what I've done here, I took the -5 minus a -7, that's my change in y, and -3 minus a -6. Here I took my -3 minus a -5 and my 0 minus a -3. So I'm just finding the slope. And my last interval is going to be, again, change in y over change in x. I get 3 minus 1 is 2, and 9 minus 6 is 3. So what I'm seeing here is that my average rate of change over these equal length intervals is the same. So what my statement is for a linear function, and this is going to be AP language, a linear function, I don't know why it keeps doing that, a linear function can be defined where the average rates of change over consecutive equal length input value intervals is a constant function. So if I were to describe the average rates of change, I would get a constant function because the average rate of change is constant, and I am looking at rates of change over consecutive equal length input value intervals. That is our AP language. If they ask you to describe or defend that a function is linear, then the reason it is linear is because the average rates of change over consecutive equal length input value intervals is a constant function. What if I look at the average rate of change over a quadratic function? Again, notice I have consecutive equal length intervals for my input values. Again, this time it is a change of 1. So if I am going to look at my average rate of change in y over change in x, I'm going to get 1 minus a -1. And my denominator, change in x, is going to be 1 minus 0. So I get an average rate of change of 2. When I do it again over the next interval, my change in y over change in x, my slope, my average rate of change, is going to be 7 minus 1 over 2 minus 1, which is 6 over 1, which is 6. When I do it again, change in y over change in x, I now get 17 minus 7 over 3 minus 2 gives me 10 over 1, which is 10. And my last equal length interval slope is 31 minus 17 over 4 minus 3. So I get a change of 14. And what I recognize is that over consecutive equal length intervals, in this case, my average rate of change is not constant. It is not a constant function. But could I describe it with a function? Well, if I look at these rates of change here, I'm again changing by 1 equal length intervals. Now my rate of change is 4 here. 10 minus 6 over 1 gets me 4 again. And 14 minus 10 over 1 gets me 4. What I recognize here is that my rate of change of my average rates of change is constant. Well, an average rate of change that's a constant function means what I was looking at is linear. So my average rates of change for a quadratic function are a linear function. They increase by a constant amount or decrease by a constant amount. My average rates of change are linear instead of my average rates of change being constant. So, again, AP language for a quadratic function, the average rates of change over consecutive equal length intervals is a linear function because the rates of change of my average rates of change are constant. So again, over consecutive equal length intervals, the rates of change form a linear function. That means that the function I was looking at was a quadratic. Now, I said we were looking at rates of change and also looking at concavity. So concavity deals with the curvature of a function. So if I have a quadratic, let's just say I have a quadratic, some quadratic function. Actually, I don't need an axis because we're just going to look at it. The rates of change, if I think about them as, because they are slopes, my average rate of change, what I was calculating over intervals, what I see is slopes. That's a slope. A rate of change is just a slope. So if I think about over these intervals looking at slopes, right? Or I could, if I make, like if I look at it, it's harder to see it here if I'm doing over an interval, but my average rate of change here versus my average rate of change here versus my average rate of change here versus my average rate of change here. If I notice something about those slopes, those average rates of change, it tells me something about the concavity. And concavity is just the, this is an informal definition, but we are talking about the direction of the curvature of the graph. So this with a leading coefficient that's positive on a quadratic, what we see is that this is concave. The concavity is the curvature is curving upward. So this is concave upward. If I had a quadratic, that was a negative leading coefficient, we will notice that the curvature here of this graph is concave downward. The curvature is down. So can I tell the concavity of a graph from a table of values? And so that's what we're going to look at here. Can I see the concavity? So the first thing that I want to look at again is my rates of change, my average rates of change over these equal length intervals. And if I'm looking at this graph just based on what I know about quadratics, what I see here at my 2.0 comma negative 2.5, I see the same values for function values, for y values, equidistant away from that. So that is going to make this point be the vertex of my quadratic. So I do see equal length, consecutive equal length input value intervals here. I'm seeing an increase of 0.4. And then I can look at my average rates of change. You can do the subtraction, delta y over delta x, negative 1.06 minus 0.06, and over 0.8 minus 0.4 is going to give me a negative 1.12 over 0.4, and I get an average rate of change of negative 2.8. And if I do the same thing here, I am going to get an average rate of change of negative 2. And if I do the same thing here, I'm going to get an average rate of change of negative 1.2. And then here, I'm going to get an average rate of change of negative 0.4. And then here, I'm going to get an average rate of change of positive 0.4, an average rate of change of 1.2, 2.0, and 2.8. And like we said before, if our average rates of change are linear, which would mean that these rates of change are the rates of change of my rates of change are constant. So if I take negative 2.8 and subtract it from negative 2, I am going to get minus a negative 2.8. I'm going to get a increase of 0.8. And if I do the same thing here, I'm getting an increase of 0.8, an increase of 0.8, an increase of 0.8, an increase of 0.8, again and again. So I see my average rates of change over consecutive equal length intervals are linear. So I see that this is a quadratic. So since my average rates of change over consecutive equal length input value intervals are a linear function, therefore y is a quadratic function. But the other thing that I should notice, why did it do that? Is that my rates of change are increasing. a negative 2.8 to a negative 2 is increasing by 0.8, increasing by 0.8, increasing by 0.8, negative 2 to negative 1.2, negative 1.2 to negative 0.4, and then negative 0.4 to positive 0.4. I start with larger negatives, and my negatives are getting smaller and smaller, which means they are increasing. And then once I move to the positive rates of change, they are continuing to increase. My rates of change are increasing. So what does that tell me about this function y? Well, if I were to just approximate this graph, let's just look at this graph at an x value of 0.4. I'm at 0.6. And then at 0.8, I'm at negative 1.6. At 1.2, I'm at negative, and then negative, and then negative. And then I see that it's going back this way. So this is way not an accurate graph. But what I see is that this graph is concave up. So it would imply, it seems that if my rates of change are increasing, the graph is concave up. And we're going to see the same kind of idea here. What I will see, though, is probably a change. If I look at this graph, my y values are getting greater and then getting smaller again. And what I notice here is my vertex right there in the middle. So when I look at my average rates of change, I will do this calculation for you. I get 1.5, 0.9. Is that 1.5 over? This is actual. Well, I'm just looking at the change in y's is what I'm doing. Since it's over equal length intervals, these will also be constant or would have a linear. So as I find these changes in my y values, what I see is positive 1.5 to 0.9 to 0.3 to negative 0.3. These rates of change appear to be decreasing. So if I actually do the subtraction, I now see a negative constant change here. So if my rates of change are decreasing, because I see a negative rate of change there, so rates of change, my rates of change are decreasing. So what that tells me here is that this function y is concave down. And if I plotted those points, I would see something like this happening, and I would agree that that is a concave down graph. We are going to look at this a little more on our assignment. That will be done in groups, and you will do some investigation that should support what I've been showing you here.